my accent, English is not my first language. Actually, it's my second, but not third. When I got the invitation, actually when I prepared this talk, I was looking in the dictionary what it means to cluster. And to cluster is when people come together. So we are clustering. And when we discuss nucleons or neutrons, which means that we're discussing neutrons coming close together, and which is very good because this is the topic of my talk. Neutrons coming close together. But since we are living in modern times, you don't just go and give a talk. You make a research. And so this is a research, at least these days. And I was very pleased with the answer that I got for what is neutron-neutron clusters or short-range correlations because of two reasons. One, there is an influence on neutron stars, and this was part of the title of this workshop, right? In nuclei and stars. So here you got stars. And then there is this generalized contact formalism, which is actually the tool that we use to study these kind of issues. So this was very successful research. Now, what? Well, I am not responsible for what is written here. Well, this is a new version. I'm with the old version. Anyway, so I also looked more seriously for relation to stars, and I give you reference to these two papers. Actually, this is very, very nice one, where he showed that the short-range correlation have an interesting impact on the cooling rate of neutron stars. And this is a very cool paper. I enjoyed very much reading it. This is more of a standard stuff, but okay, it has neutron-neutron short-range correlations, so I could not resist it, but put it here. Anyway, back to clustering. So this is a cluster. What we are going to discuss is not just a cluster, but actually short-range correlation. And short-range correlation is when subgroup in this cluster is getting closer together. In this case, this is two-body cluster, which of course is very important to these systems. But think about more physical system, ideal gas. Okay, in ideal gas, what you have in mind is that you have particles that are roam together in space and actually never interact with each other, which means that they rarely interact, they rarely have this short-range correlation, but you understand that all the properties of the system are completely governed by this short-range correlation, by this very rare event of two particles interacting with each other. And moving on to quantum mechanics, when we are now discussing correlations, it is actually what is going to happen to the wave function when two particles just coming close to each other. And in this case, we have a situation that if you have a two-body system and the distance to the particle goes to 0, you will have some function that describe what happens when these two particles come close to each other. Let's assume that we are discussing low energy dilute system. So when we are considering a many-body system and two particles within this large system comes close to each other, we expect to get the same situation. That is, the wave function of these two particles within the larger system will behave just as the wave function of the two particles when they are isolated and nobody is around. Very much, the example that everybody likes to give is like we have a couple which are in love. A couple in love, you can see that they are in love, whether they are alone in the desert or in a room with many people. They always behave in a very distinct way. The same way, it's our beloved two particles. And it's, of course, true in configuration space. And then, if we have this kind of a property, short-range observables have a very nice feature because the matrix element of short-range operators becomes almost independent of the properties of the system. Actually, it's factorized into a universal matrix element times a coefficient. This coefficient measures actually how many short-range correlated pairs we have in the system. And we call it the contact, the invention of Shinatan. So this C counts how many correlated pairs we have in the system. Two body, it will be just C2, and in general, some Cn. And of course, the same goes if we move from configuration space to momentum space, and we have essentially the same situation, but this time instead of two particles coming together, the relative momentum goes to infinity. But this coefficient, which is called the contact, is again the same coefficient. The same coefficient of correlated space as in momentum space. So with this observation, we understand that high momentum observables, which are usually the pain of people doing many body calculation, can be easily accounted for. Because we know that if you have short-length observables, then this factorization should come out, and we can use this contact formalism and calculate such observables. And on the other end, the number of correlated pairs, this is something that in principle is low energy property. Therefore, we can calculate it using low energy theories like effective field theory and standard many body methods. With this in mind, I will tell you that this story has a long history in nuclear physics, starting with the works of Levinger in, 61, 51. Actually, I had the honor to spend an evening with him. Many years ago, actually. But there is ongoing work since then. But the way things were formulated in a modern way were actually not in nuclear physics, but in atomic physics, the work of Shinatan. And he observed that some properties of ultra-cold atomic systems can be related to a single number, this C, the contact, that measure the probability of spin up, spin down atoms to come close to each other. And with that, he realized that the momentum distribution would be this contact divided by k to the fourth, and he has some relation to the energy and the way the energy change when you play with the scattering length of the system. All these nice formulas were actually proven experimentally. If you note, there is a plateau here and plateau here. This is the momentum distribution. This is the RF response of the system. And you can see that it is the same number that appears here, the same number appears, and this number is just the contact for this specific system. Now let's move from atomic physics to nuclear physics. Of course, everything in nuclear physics is way more complicated. That's the beauty, right? And what we try to do is to generalize this idea and apply them to nuclear physics systems. And of course, when we do so, we call it a generalized contact formalism. This is the GCF that Google was kind enough to present to me on the second slide. And the idea here is that in nuclear physics, we have to count not only the fact that we have short-term correlations, but it could be different kind of pairs. It could be a neutron-neutron, neutron-proton, proton-proton pairs. Then they have different quantum numbers, different spin, different isospin, different angular momentum. And if you want to write things in the more general way, then you have to account all of these things. And then you will realize that you don't have a single contact, but actually an array of contacts. Everything becomes much more fun. And this function is not given you by some universal law, which provides this 1 over k to the fourth tail, but it should be the solution of the zero energy two-body problem. And if you do that, you get a very decent description of the many-body problem, at least asymptotically. And this is what I will try to persuade you in the next few slides, but just a few more words about the formalism. So you have an array of contacts. You can define them through the normalization of your wave function. And if you're looking for the fundamental ones, so we have, we need to consider only pairs with relative L equals 0 angular momentum. And if we do that, there are only 4 possible configurations, right? Either proton-proton, neutron-neutron, neutron-proton with spin 0, or the neutron channel where you have neutron-proton with spin equal 1. These are the only possible configuration. And if for some reason the system admits isospin symmetry, you have at the end of the day only 2 contacts, one for the neutron channel, one for the spin 0 channel. That's it. And actually it doesn't. This we'll see later. This idea was applied to many, many things, and I will show you some examples. So the first thing is the momentum distribution. You can think about one body momentum distribution or two body momentum distribution, which is describing the relative motion of 2 nucleons. And using this idea, you can write down a very interesting relation. That is, that the one body momentum distribution becomes asymptotically a sum of the, okay, in this case, if this is the proton momentum distribution of the proton-proton and the proton-neutron, here you have a factor of 2. And this is a universal relation. This should hold regardless of what is the potential that you are using. The same is for the neutron. And as you can see, this is exactly the situation that happens in numerical calculation. When you try to analyze the tail of the many-body wave function and compare the one-body and two-body momentum distribution, they exactly fulfill this relation. Then you can use it further and predict the behavior of the one-body momentum distribution, because you know your asymptotic functions, and you can write down the formula of this form, and when you apply it to all these nuclei, you can see that within something like 10%, or maybe a bit more, you can describe this momentum distribution from the Fermi momentum up. So, and okay, we can do the same game now for the configuration space and describe the two-body density, which is the probability of finding a neutron away from a proton or a neutron away from a neutron, or vice versa. And as you can see, regardless of the interaction that you are using, all these wave functions collapse, all these density collapse into a single line when the two particles come close to each other. So I think this is quite reassuring, and with that, we can actually go and try to describe even the full two-body density. Here it is composed of different contributions. Short range is what you got here. And with that, one can also extract the contact, which is the probability of finding correlated pairs. But I will not go into details here. Now, some words about numerical verifications. As I was saying, we have neutron-proton correlations, proton-proton correlation, neutron-neutron correlation. Actually, in this type of in the experiment verification of these ideas, so far, we have 0 to very little information about neutron-neutron pairs. We have quite a lot of information about neutron-proton pairs because they are very dominant. And we have nice amount of information about proton-proton pairs. 3-body correlations, which is, okay, the next question is now the front line in this kind of research, but we will not discuss it. So the way to, or the most popular way to study this correlation is by electron scattering. There is this magic number, which is called the Bjorken X, that if you dial it between 1 and 2, you are sensitive only to 2 body correlations. Between 0 and 1, this is 1 body physics, 1 and 2, 2 body physics, 2 and 3, 3 body physics. So with that in mind, people went and did electron scattering on different nuclei, and you can see that about this X Bjorken 1.4, you have this plateau. This is the ratio between the general nucleus, A body cross-section, and the neutron cross-section, and you see the plateau. It means that in this place, the cross-section behaves actually like the neutron cross-section, being dominated by 2 body physics. There are even nicer pictures than that. I just don't want to go into too much detail. This again, the ratio between finding proton-proton and finding neutron-proton. Lines are the GCF theory. Crosses are from the PhD work of Igor Korover. Then we apply it to other electron scattering experiments, and you can see that the comparison between theory and data works very nice. Actually, it is almost illegal what's going on here, because the momentum range or energy range, where it is still giving a reasonable description, is way beyond the reasonable limits of this theory. The theory should not work there. Still, you get a nice agreement. Anyway, having said that, there are a few observations about short-range correlations that we know by now. First of all, this is not a combinatorial business. The number of correlated pairs is not the number of pairs. Actually, it grows linearly with the number of particles. And think about it, just how many neighbors you have around you. It doesn't depend quadratically in the number of people, but actually it's linear, goes linearly with the number of people. Then the majority of short-range correlation pairs are Newton-like pairs, spherical one, and this is due to the tensor force in the acting in the nuclear physics. And okay, you can see these two pictures. Now, let me go to the title of my talk, which is neutron-neutron correlations. And for that, what we did, we actually went to the extreme, saying, okay, if the number of pairs is independent of the force, then maybe a mean field description of the nucleus will be a good enough starting point to count the number of correlated pairs. Sounds like a contradiction, right? Mean field have no correlation. How can I use it to count the number of correlated pairs? So bear with me. So first of all, I refer to this work that we did with a group of very smart people that actually do an honest-to-God calculation. And you can see that with all these nuclei, the contacts are independent of the actual interaction. There are some variations, but in general, there is very small sensitivity to the actual interactions. Some interactions are very soft, the other are harder, but in general, the contacts are almost independent of the interaction. Then, if we are interested not in the absolute value of the contact, but not just in contact ratios, we can make the following conjecture that contact ratios that are proportional to short-range, to observables of short-range operators should also get a good description if instead of very sophisticated, very elaborated wave function, I will be using some mean field shell model wave function. And actually, the first to suggest that was Yigal Talmi. Some of you may know him. We celebrated his 100th birthday this year. And he's still well. He has very good stories about what happened 70 years ago. Short-range memory is always a problem. But he suggested something like 6-7 years ago to use this idea, but it took us some time to believe that this is a reasonable idea. And after we did this work, we thought, okay, let's move this way. And then we did it. It's not a very difficult calculation. The only thing that you need to do is write your Slater determinant and calculate the expectation value of a delta function. And at the end, this is just this integral that you need to calculate, one three-dimensional integral. Not that complicated, and then you can separate it into angular part and radial part, and the angular part you can then solve many 6J, 3J, all this NJ technology, and you get what you want. And at the end of the day, you can calculate the contact through these sums over all occupied states. After we did it, what Raz Yankovic, which was a student in charge of this project, that actually you don't even need to do the angular integrals. You can just replace every angular integral by 1/4 pi, and you get an accuracy of the order of 1%, which is very satisfying for this project. So we worked actually too hard for this problem. And then the question is, how good is this approximation? So we can compare to extraction of the contacts from different places. So the first thing that we did is to compare our proton-proton contacts with what we previously extracted from charge density, both experimental and from VMC calculation. And this is what you see here. The shell model, this mean field calculation, is the black points. What we had previously is the blue points, and you have very nice agreement. Then we went to electron scattering. In the case of electron scattering, there is a quantity which is called A2, which is the ratio of the inclusive cross-section to the neutron cross-section. And this is what you see in the lower figure here. And okay, this is normalized by the helium-4 contact, but you see that, again, there is not too much details in this picture, but this model captured these features very nice. So this was reassuring that we are not completely off. Then we can finally come to the title of this talk, which is the neutron-neutron contact. What is the probability of finding two neutrons coming close to each other? And this is what we plot in this picture. In blue, this is the chance or the probability or of finding two neutrons, related to neutrons in the nucleus. Okay, everything is normalized by the number of nucleons. Black is neutron-proton pairs with spin equals 0, and red is the proton-proton. So we see, but this is in some sense very reasonable. The larger the nucleus, there are more neutrons, then you expect to see more neutron-neutron pairs. But okay, that was nice to see. Then we try to analyze it a bit to understand why we have this behavior. Because nobody discussed this before us, so it was reasonable to get some analytical feeling for what is the reason to have this behavior or the systematics of the contact with N over Z. Then we came with a very simple model that I attributed to Levinger because it is based on ease analysis. So think that we have some volume, and this volume we have two particles of type A and type B. 5 minutes, fantastic. And I have Na particles of type A and B particles of type B, and the volume is this delta omega. And let's assume that if the particles come within some small volume close to each other, I will say that they are correlated, okay? In this case, it's very easy to count the number of correlated pairs, right? Classically, it would be just this number, which is the product of this Na and B, times the relative volume that I call it correlated pairs. Make sense? Now what I need to do is just to integrate over the whole volume of the nucleus, which is what I'm doing here. On the way, I will replace this V by L just to honor Levinger, and I will assume, something which is very reasonable, that the densities inside the nucleus are more or less constant. So I get this kind of formula for my contact, which is a coefficient, which I don't know, density of particles A, density particles B, times the overlapping volume between these two particles. Reasonable. So we applied it to our calculations, and okay, this is the way the final formulas look, and actually it reproduced very nicely our calculations. This was cool. But then something interesting happened. There was this group of Liang et al. That were calculating the contact using R3-Fogg-Bugel-Lyubov method, more sophisticated than what we do. And I happened to be the referee of their first paper. Happens. And they tried to fit their calculation, this type of line, with some approximation. And I asked them, maybe you will look at this formula, might be useful for you. And they looked at it, and they liked it. So what you see is a second paper that they produced, and dots are their calculation, R3-Fogg-Bugel-Lyubov. The lines are these formulas. Fantastic agreement. And then they just scanned the whole nuclear map, and you see that this L0NN is this one, and covering almost, okay, all reasonable nuclei, it changed by nothing more than 20%. Fantastic description of all possibilities. And then they were actually very kind because they call it universal law for nuclear contacts. And what I really liked is that we have the YPB laws now. So with that, I will finish my talk. What I try to present to you is the notion of short-term correlation within the nuclei. As you have seen, they play some important role in the stars, both in cooling of neutron stars, also in the equation of states. Using the factorization ansatz, which separates the short-range physics from the many-body physics, is actually rather simple to describe this very difficult process like electron scattering at high momentum or nucleus scattering at high momentum. And funny, all these ideas are working very nicely. The front line in this subfield of nuclear physics is three-body correlations. And from the experimental point of view, we have very little information about neutron-neutron correlations. So with that, I will thank you, and yeah, the most important one, sorry, thank you. this is really the group of people that collaborated on this project. These are the current students that work on the project. Raz, that this was his master thesis. Sar, that just finished his PhD, and Nitzan, that finished his master's and go to PhD. And Bezalel Bazak and Ronen Weiss are the two guys that with whom we started this nice journey. Bezalel is faculty in our department. Ronen is coming to Israel back once Sauri, where is she, let him go. And he will also become a faculty with us. So that's the story of this project.
To compute those constants,
Yes.
you need an operator. Doesn't matter the operator you put there.
Well, we calculate ratios. The
Yes,
ratio
but
doesn't matter what you put
matter.
inside. As long as it's short range.
Yes, this is what I was curious.
Yeah.
Doesn't matter the operator.
No. Take whatever short range operator that you like. That's good enough.
So Nir, this thing with short-range correlations is very old, right? So you already pointed to Levinger, 50s. People are thinking about this in the 50s.
Yes.
And then I think the most beautiful chapter was the Bethe-Goldstone equation, which shows that when two fermions scatter in a fermion sea, Pauli blocking has a huge effect. And for nuclear physics, the hard core is healed after a while. It's called the healing distance, which makes the shell model works. Otherwise, the shell model would give infinite energy, right, because of the hard core. But because of this healing distance, everything gets like free neutrons, free protons after a while, right? Like this formula you put there in green, right?
This is the picture that you had in mind.
Yeah.
So the red line here is variation Monte Carlo calculations.
Right. So
okay?
my question is not that. My question is the following. So now we are talking a lot about short-range correlations. People have already tried this in the past, a lot of calculations, maybe like yours, not like yours because you are trying to count the pairs and so on. But there were calculations with Jastrow things to minimize the variation of Monte Carlo and so on. But what I would like to know really is what are the source of the short-range correlation? How does it arise from QCD? Okay, that's what would be something which is really for me interesting, Neil. How does the gluons and because you have this 0.4 Fermis. So 0.4 Fermis means that the nucleons are basically overlapping. The quarks must know about it, right? The quarks and gluons must know about it. What does it mean, 0.4 Fermis, when they are, it must be quarks and gluons there. How QCD treats this, right? I'm sorry, this is a little bit different than what you
No, it's okay.
you are looking here, but that's very interesting.
There
right?
is an interesting paper. The names of the authors just escaped my mind. Where they analyzed the EMC effect, which is the structure function of the proton, okay, within a nucleus, and there, starting from QCD argument, they show how there is a term which is proportional to the density and is affected by nearby objects. And I think this is the closest that we have to answer your question. And this is very much, I think, what they predicted was later realized experimentally.
But as I understood, your work is more how you count the number of pairs and short-range correlations, how you count
You
this.
can come either from the nuclear physics many-body point of view, which is what we did, or start from QCD, but you will reach more or less to the same conclusion. But one way might be longer than the other.
Mhm. Sorry, I deviate a little bit
No,
from
no, it's okay.
questions. Bira has a question.
I have another one. You have?
Oh,
Okay.
somebody has a question.
Yeah, we can also go and have coffee. That's okay.
Well, if you want, we can go for a coffee. But yeah, thank you for your talk. And I'm here thinking about there is maybe ways to get this information about pairing, studying the two nucleon transfers. Do you have any thoughts about that? I mean, because if you consider two nucleon transfer, if it's simultaneous transfer, this might give you some hints about this pairing between these two transfers. I know that we might have talking in different regimes here, but is your theory or your formalin also applied for reactions as well?
Yeah. I guess that if you have a good neutron detector and
I mean, in this case, I mean, I'm considering, well, actually, I'm going to present this Thursday, that we can study the two neutron transfer, and from the cross-section, if we can tell more or less if it's simultaneous or sequential, and if it's simultaneous, maybe this could be linked with the pairing between these two particles.
the question,
But, well, I thought that coffee would be good. Sorry.
okay. Anyway, the point is that
But
the relative
my
momentum
point-
should be higher than the Fermi momentum. Otherwise, you are not in the right regime. Twice the Fermi momentum is even better.
Mhm.
Otherwise, what you see is something else.
Mhm.
Okay?
We are talking here about a two-particle correlation, but can be 3, 4-particle correlation, even higher.
Yes, of course.
We observe alpha transfer. So somehow the problem was performation of alpha in order to be transferred. So, for sure they should be correlated or not. You can calculate again. They transfer alpha immediately, or they transfer to protons and then to neutrons. So
The question, what I find appealing in this topic is that universality that comes from this factorization. And this universality comes from the fact that you're actually looking at very high momentum or very short distances. I'm not sure that the situation with the alpha particle is the same.
no. I'm not saying that it's the same. I'm saying that you see again also.
Definitely you see that, but I'm not sure that this is the same physics. About 3 body short-range correlations, we are struggling with that. The experimentalists are trying to measure that. Okay, the amount of events is very little. Hopefully, within the next few years, we will get more insight into that. From the theory side, there are few works. We also try to push it. There were, okay, I think, Ronen, with Stefan Gandolfi, and Leonardoni, Diego, put one paper on the archive, published one paper last year. Other groups also did some contribution, but situation there is not, still not a very nice formulation of what's going on there. There is a gap that we need to cross.
Okay, we'll have more chance to discuss this problem during the discussion session. It's very interesting talk. Thank you very much,
Thank you,
Nir.
Welcome.
There will be a discussion section, maybe 15 minutes, 20 minutes at most.